let's say 12-volt battery. C1 is 4 microfarads. C2, 6 microfarads. C3, is 8 microfarads, and then C4 is 5 microfarads. So let's say you have some random capacitors. So this is kind of like your generic kind of circuit where you have some parallel capacitance going on and you have some series. So you got to break it down, find the combined capacitance. So we can ask a variety of questions, but the typical questions are going to be find the total capacitance, C total, find the charge total flowing through the battery, find the total charge that the battery, in other words, the total charge that the battery has supplied to all the capacitors combined. The total charge that battery has supplied to all capacitors. And we could also find the total energy that the battery has supplied. So same idea. And then we can break it down and ask for the charge of each particular capacitor. ABCD, what's the charge of the first capacitor? What's the charge of the second capacitor? The third capacitor, the fourth capacitor, and then the voltage of each one. And ABCD, F, and then the energy of each one. Okay, so we're gonna combine these in series and parallel. So which one should we do first? So over here, you look here to see that two capacitors are in series. Immediately, that kind of is what stares at you first. These two are in series. So before saying that this is in parallel with that, you have to do this series first, then you can do the parallel. So it would be the mistake, for example, to say, oh, this is in parallel with that and this is parallel with that. No, that's wrong. This is in parallel with the combination of these two, right? So you have to first find the net capacitance of these two. So you're gonna, the next step, therefore, is to call these two C prime. So in each stage, you are reducing the circuit to a more simple looking circuit, you see. So now these two combined is C prime. So now find the value of C prime. So you can do, these two capacitors are in series, right? So you can do 1 over C prime is 1 over 6 plus 1 over 8. And then combine them together, you get 8 plus 6 over 48. And then that's 14 over 48. And then reciprocate them, 48 over 14. So then that's going to be 4 goes into 22, 24/7. So we could leave that as 24/7, right? So then you have here 24/7. So this is equal to 24/7. Okay, then you're going to say these two are in parallel. So you can't say this is in series with this. This is in series with the combination of this, you see. So you have to do the parallel first. So So this is going to be C double prime. Okay. So then you're going to add these two. These are parallel. So we could just simply add them, right? C double prime is equal to C prime plus 5. So then add 5 to this. Okay. And you get 35 plus 24, 59 over 7. Of course, these are all going to be microfarads, right? So that's going to be 59 over 7. Okay, then these two are in series because it's just a wire. So it doesn't matter that it has a corner there. It just comes and flows through. So the charge just goes like this. So they both have the same charge, right? So they're going to be in series. So the last step is to call this C total, and then add two capacitors in series. 1 over 4 plus 1 over 59/7. So it's always 1 over this plus 1 over that. So it goes like that, and then the 7 goes to the top. Then you cross multiply. You get 1 over C total is going to be 59 times 4. So 59 times 4 is going to be 236 on the bottom. And then on the top, you're going to get 59 plus 28. 59 plus 28, 87. And then reciprocating in. So now you're going to have C total is the reciprocal of this, which is 236 over 87. So some weird number, huh? Okay, so now that's going to be that C total. So now I can say, okay, how much charge would that battery give to that total capacitance? Then we can start working our way up again. So what would Q total be? Q total would be C total, V total, right? So then Q total would be 236. So let me circle all the answers we get along the way. Oh, this is microfarads. Okay. So then you have, so 236 over 87. And then this is 12. Okay, so 236 times 12 divided by 87. Okay, so 32.5517 microcoulombs. Okay, so that means that battery will supply the net capacitance of all of them, 32.5517. And the energy that the battery will supply to that, the total energy, is half C total V total squared. So half 236 over 87 times 12 squared. So that's going to be Uh, instead. $195.3103 microjoules. Okay, so that's the total energy supplied by the battery to the circuit, right? Okay, now let's go backwards. So then we're going to argue that this capacitor is the net capacitance of these two in series. So they have the same charge as this guy would. In other words, if the battery is going to supply this with that much charge, it would supply that with the same charge, and this would also have the same charge because the charges in series are the same. So the charge here would be 32.5517. So now I'm going back up to the top, and then the 32.5517 microcoulomb. So that means I already know the answer to the charge of one of the original capacitors, right? Back all the way up to the top. So that is its charge. And if I want to know its voltage, what would I do? I would take let's see, voltage is Q over C. So then I would divide this by this, right, to get the voltage. So 32.5517 divided by 4, 8.1378. Okay, so then this is the voltage of that guy, and this is the charge. So I already know. And if I wanted to get the energy of that one, right, then of course I could get the energy. Well, let's do the energies all later. Then once you get the once you get the charge of that, okay, what else? Oh, what's going to be the voltage of this guy? So there's two ways I could do that. I could say, oh, okay, I know its capacitance and I know its charge. Then I could say charge divided by capacitance. Okay, then I could divide this number by this number to get its voltage. Or I could argue that the voltage of that should be whatever number is needed to add to this voltage to give you 12. You see? So the voltages of each one add up to give you that. So then I think that's just easier to say 12. There is going to be slight rounding here, but it's minimal since I'm going 4 decimal places. So 12 minus 8.1378, 3.8622. So, okay, that gives me the voltage of this guy. 3.8622 volts. Okay, so now I know its charge and I know its voltage and I know everything, right? So now I go one step up. Okay, so then what am I going to say? This is the net capacitance of two capacitors in parallel. So the voltage it has is the same as the voltage that these guys have. So the voltage of this guy is 3.8622. And then the voltage of that guy, 3.8622. Okay. Well, now this is one of my fundamental answers because it was originally one of the capacitors. So then if I know its voltage, I can know its charge, right? Charge is capacitance times voltage. So this guy times this guy gives me its charge, right? So 3.8622 times 5. So its charge is going to be 19.311 microcoulombs. Okay. So then I've got its voltage, I've got its charge. Then I can do the energy later on. And then how about the charge of this guy? Well, again, I could say two ways. I know its voltage and I know the capacitance here. So I can multiply them. Or I could say, take the charge that's here, subtract it from the combined charge. So this one had how much charge? 32.55, you see? This is the combination of these two. And therefore, whatever charge this has to have the rest of the 32, you see? So versus multiplying them. So you really got to know what adds up and what's the same. And that's kind of what you're using here. So then you're saying, take this charge, subtract that. So 32.5517 minus 19.311. Okay, so then that's going to be this charge, right? So I'm going to say 13.2407 microcoulombs. Together added up, these two together added up give you that charge. These two voltages are the same. So far, so good. And then we just got to go one more step back. Right, one more step back, and then what are you going to say? The charge that this guy has, these two are in series, right? So they're going to have the same charge as that, 13.2407. So this one is going to be 13.2407 microcoulombs. 13.2407 microcoulombs. And now what are their voltages? We can find one of them, like let's say this one. So I could say voltage is charge over C. So then I could take its charge and divide it by that C. What was the C3? I think it was 8. Yeah, it was right. It was right here. Okay, so take its charge divided by 8. So 32 divided by 8. So then the voltage here is going to be 1. Let's write that with a different color. 1.655. And maybe one more. 1 volts. Now you're going to argue that the voltage of 2 should give you the total voltage of that. So then you subtract this minus this to give you the voltage of that. Right? So this minus this, 3.8622 minus 1.6551. Okay, so then this is going to be 2.2071 volts. Okay. So far, any questions? Or is that like a lot? Seems easy. Seems easy when someone else does it, huh? Okay. Okay, then the next thing is, I guess, the energy, right? Let's do the energy of each one. So the energy U1, right? So we could use any of the equations for energy, you know. What was, let's see, half C1 V1. I think this one is probably one of the easier ones because I already know its capacitance, what its capacitance is. So I can just say half. The C1 was 4 microfarads. V1 was, I wrote them here. Yeah, right here. 8.1378 squared. Potential energy of the second one, half. So what then is C2? 6 microfarads. What is its voltage? 2.2071 squared. Okay, so I'm just taking this version of the equation, half C1 V1 squared. Okay, C1 is 4, and then its voltage is that. Then the C2 is 6, its voltage is that. What's C3? C3 is 8, its voltage is, C4 is 5, its voltage is 3.8622. Now, if I did it right, what should happen? Well, energy conservation tells us that the energy that the battery has supplied to all, in other words, the energy that the battery would have supplied to the combined capacitance of each one, you would have supplied it with that much energy, right? 195. So then if I combine the energy that each one has, remember that the energy equation comes from how much work it takes to charge each capacitor. So if I take this energy and split it with all of them, they should all add up to 195. So if I've done it right, that's kind of your ultimate test, right? So here's going to be 2 times 8.1378 squared. Okay. 132.4476. Okay, and then this one is 3 times 2.2071 squared. 14.6139. Then this one is 4 times 1.6551 squared. And then 2.5 times 3.8622 squared. Okay. So now the ultimate test is what? Add up their energies. Usually if this works, that means basically everything you've done up to that point, you are correct. You know, if you add them all up, the energies of each capacitor, and they should give you 195. There we go. So much glare. I have a glare thing, but find it. Where was that? I'll find it later, probably. Oh, here it is. I think this helps slightly. Yeah. No, not there. It's got to be here. Yeah, but then how am I going to push the buttons, right? Okay, so then 132.4476 plus 14.6139 plus 10.95 plus 2915. Oh, very close. Within the fourth digit was only slightly off. Nice. Perfect. So energy conservation holds true. The universe is still functioning. Yes, yes, yes. Okay. Okay, so I'm kind of introducing you different kind of capacitor questions. The first one was like the one that you saw earlier where you say, oh, okay, take a capacitor, put in a dielectric, take it out, see, connect the battery. The other one is to say, like capacitors in a circuit like this. Then you've got another type. Oh, I can build one right off this example. Oh, you know what? Let's do this. Let's build one right off this example. We can say, for example, let's take this circuit. We can say, so imagine in this circuit, the energy of the energy stored in the fourth capacitor, how many times greater is it than the energy stored in the third capacitor? So the energy of the fourth divided by the energy of the third, to give you an idea. So the capacitor number 4 has how much more energy? It looks like it's about 4, but close to 4, but not quite 4. 37.2915 divided by 10.9574. Oh, it's not even, it's about 3.4. Right, so the capacitor 4 has 3.4 times the energy. So let's say for some reason I wanted this guy to have 4 times as much energy as that, to store 4 times as much energy. So what would I have to do?